So last time we talked about a chemical vapor deposition. This lecture we will talk about a physical vapor deposition. So there are two types of the physical vapor deposition. That is the evaporation and the subaqueous deposition. So by the meaning physical vapor deposition, that means normally there is no chemical reaction. So no chemical reaction involved. But sometimes there can be some chemical reaction. For example, for the subaqueous deposition, subaqueous titanium nitrate. When we do the subaqueous deposition of titanium nitrate material, so we can use titanium nitrate target. We can also use titanium target. If we use titanium target, we will add nitrogen into argon. So normally when we do the subaqueous deposition, so we use argon to get titanium nitrate film using titanium as the target. We can add nitrogen into the argon to get titanium nitrate film. So this is called reactive subaqueous deposition. So here is the comparison of the evaporation of the subaqueous deposition. So basically you can think of this way. So here we have like a gold, a material. We have the wafer here. So how to create a gold atom? How to create a gold atom? So one way is by the heating. We can heat the gold, so the gold will be vaporized gold atom. Another way we do the ion bombardment. So we can use argon ion to bombard the surface. When the surface is bombarded, so the gold atom will also be emitted. So this is the evaporation, and this one is by heat is evaporation, but the argon ion bombardment is the subaqueous deposition. So this one for the evaporation we need a high temperature. For the subaqueous deposition, normally it is done at the room temperature. We use argon ion. So we have argon ion ionized to bombard the surface. So we have a plasma. So we have the plasma in the chamber. So normally the argon pressure is 5 to 50 milliliter. But for the evaporation, the evaporation is done in a high vacuum. So the film quality for the evaporation is not as good as the subaqueous deposited film, because for the subaqueous deposition, so we have bombardment with ion. This is energetic process. So when we have actual energy provided to the deposition, we get better film quality. So the film thickness is monitored by the quartz crystal balance. For the subaqueous deposition, we do not need to monitor the film thickness, because the film thickness is very reproducible. When you have the recipe, the deposition rate will be almost fixed. But for the evaporation, a tiny change of the temperature can lead to a big change of the deposition rate. So as a result, we need to monitor film thickness. We cannot rely on the condition of the deposition. So here is the schematic of the evaporation. So we have the source, where the source material will heat up and it will be vaporized to form on the wafer, to form the film on the wafer. So this is done at a high vacuum, normally less than 10 to minus 5 torr, because we need to avoid collision. So we need to minimize the collision. So that means the atom comes from here to here without collision with the molecule in the chamber. So the heating is done by the relative or electron beam heating. So the surface reaction is physical. It can be very fast, can get to 1 micrometer per minute deposition. For the subaqueous deposition, normally is about 10 nanometer. For subaqueous, 10 nanometer per minute. For evaporation, we can get to 1 micrometer per minute. So the snaking, we have very high snaking coefficient. That means if the atom comes to here, it will stay here without move around. No move around. This is called a high snaking coefficient. It comes to here and stay here, not move around. So this gives you poor conformal coverage, but this is good for the lift-off, because we can see this case. This is the poor conformal coverage. We have deposition along the horizontal surface, but no deposition along the vertical surface. So this is a poor step coverage, but this is good for the lift-off, as we have seen before. So evaporation is not as widely used as by the industry as subaqueous deposition, but actually it is used for some, for example, for the we know right now we have the LED light bulb. So the chip here, the LED light bulb, the chip is fabricated by the evaporation. It is done by the evaporation. So we have the gold. We have gold electrode for the LED light bulb chip. This one, the gold electrode here is done by the evaporation and the lift off, and by the evaporation and the lift off process. So here we said that we need a high vacuum to minimize the collision. So how high vacuum we need to eliminate the collision with the gas molecule. So then we need to know the concept of the mean free path. So we know that if we have the oxygen gas, for instance, if we have oxygen, I draw it here, oxygen gas molecule, it will come to here, then there is a collision, it comes to here, then another collision comes to here, then another collision. So the mean free path is from here. So this is the mean free path is called lambda. It's the average distance between collisions. So now we can estimate the mean free path. So here we assume the diameter is sigma. Then the other gas molecule is also sigma. This one, the diameter is also sigma. As you can see, within the cylinder of 2 sigma, so every molecule that is inside here, there will be collision. So the diameter is twice the diameter of this particle, because the other particle also has a diameter of sigma. So during time dt, so the collision volume swept is given by a pi sigma square v dt. So v dt is the vertical travel distance. Then the number of the collisions during this time is given by the pi sigma square v dt times number that n over v is the number density. So we have so many collisions within the delta t time. Then the mean free path is given by v dt is the distance traveled divided by the number of the collisions, so given by this formula. For the more rigorous treatment, so we know we have actually if you remember for the gas, so we have something called Maxwell distribution. If we use the Maxwell distribution, so we have extra term here. We have extra square root 2 here. So this one similar to this one, but here we have extra term with square root 2. And we know that, so here we have the PV equal NKT. Then N over V equal to P over KT. N over V. So then in the end you get this formula. So you can see the mean free path is proportional to 1 over pressure. So the lambda and the P times lambda pressure times mean free path is a constant. For example, it is for the air is 7.8 10 to minus 3. This may not be. This is for a particular gas molecule. So here we assume sigma equal to 3 angstrom. So we get this formula here. So now we can do some estimation. If we want lambda to be 30 centimeter, then P is given by this number divided by 30, which is the 2.6 10 to the minus 4 torr. So typically, when we do the deposition, we have the vacuum better than 5 times 10 to the minus 6 torr. So then there will be no collision. So the molecule will come from here to the wafer without collision along the path. So this is the mean free path for the different gases. In this case, you can see atmospheric pressure 760 torr. The mean free path is about 40 nanometers. But you can see in this case, the mean free path is this one. We use lambda. We also use lambda. So lambda L times pressure equal to pressure times distance equal to 3 minus 3. So this number here corresponds to the case of the water. Corresponds to case 3 times 10 to the minus 3. For the high vacuum, that is 7.6 microtorr. The 7.6 microtorr is 4 meters. So this is much larger than the size of the evaporation chamber. So typically for the spatial deposition, we have argon pressure is about 7.6 milliliter. Then the mean free path is a few millimeters. So then there will be collision. So in a spatial deposition, there will be collision by the argon molecules. Another concept is the arrival ratio. For example, so we have aluminum. So here is the case for the aluminum film. We have the wafer here, and we have the deposition. So this deposition gives you 1 nanometer per second. So this corresponds to 6. Maybe you can do the calculation. That gives 6 10 to the power 15 items per square centimeter per second. So we have 6 10 to the power 15 items, aluminum items per square centimeter per second to give 1 nanometer per second deposition rate. At the same time, we also have the gas molecule. For example, there is some oxygen. We have some oxygen here. This oxygen also collides with the wafer surface. The ratio, so the arrival ratio equal to 1 means the number of the film molecules, like aluminum, hitting the surface per second is the same as the number of the gas molecules, like the oxygen. This is the definition of the arrival ratio. So how much? So we know this one is 6 10 to the power 15 atoms per square centimeter per second. How much oxygen will hit the surface? This one is given by 1/4 NV. So N is the number density. Is the number density equal to P/KT. N is the same as here. So this is N. Here, N/V is the same thing as here. N is number, that is P/KT. So V, what is the speed? So what is the speed of the gas molecule like oxygen? So we know that roughly we have this one, mv squared equal to 3/2 kT. So this is the basic formula. 1/2. This is the mass of oxygen, and kT, K is Boltzmann constant, T is temperature. Then we know the weight. The weight equal to 3 kT/m. Then we know the N, and the N equal to P/KT. So weight equal to this one. Then we can also calculate the arrival. Then we can also calculate how many gas molecules hit the surface per second. So this depends on the pressure. So you can do that. You can show that at this pressure 10 to the minus 5 torr, the arrival ratio is close to this number. So we have arrival ratio about 1. So you can imagine if we do the aluminum deposition, when we have oxygen, then it will form aluminum oxide film. And this is not good. So normally we need the arrival ratio to be at least like 10 times. This way the film will be pure. But this depends on the film. For example, titanium will react easily with oxygen. Then it forms the titanium oxide. So actually, we can use titanium as the pump. It's called the titanium pump. So what do? We shoot titanium vapor into the chamber to react and trap the gas molecule to have higher vacuum. So this concept goes the arrival ratio. So typically we need this vacuum so that we get the film. We have 10 times of the film than the gas molecules. 10 times of the film material than the gas molecules hitting the surface. So now we look at evaporation rate. So here one example is the point source. So R is the evaporation rate. And that can be atoms or grams per second. You can imagine if we have like a gold, we evaporate along all the direction. I will draw a circle here. Then the flux here is given by R divided by 4 pi r squared. So the surface area of the sphere is 4 pi r squared. So the total evaporation rate is R. Then the flux here is given by R divided by 4 pi r squared. You can see here. This is the flux. So flux is flux. This can be the atom or gram per square centimeter per second. You can see here R evaporation omega over R square. For the case of if the source emits in all directions, omega equal to 4 pi. Omega equal to 4 pi. Otherwise, if it emits only upward, then this term omega equal to 2 pi. So similar to this idea. Then the deposition rate is given by this number here divided by the density. N is the density of the material, can be atoms or grams per cubic centimeter. We have also got term cosine theta K. So this term here, because this is the film on the wafer, so this is the flux on here is given by this one. We have a term cosine theta K. So we have cosine theta K here, because the film on the wafer thickness will be smaller than the film thickness in this case. So this is the point source. Another possibility is called the small surface area source. So here we have a small surface. So this is the source. Then the flux is given by R equals 2 pi. So here omega equals to 2 pi. Because it's only upward pi square. Here we have cosine theta, we have this actual term. So you can imagine when theta I equal to 0, we get the maximum. So that means that we have more emission along this direction. When theta I equal to 90 degrees, no emission, 0 emission along this direction. At the given theta I angle, the emission along this direction is given by cosine theta I n power n. Then the deposition rate is given by this number divided by the density, and also times cosine theta K. So this is the same thing, cosine theta K, same as here. So we can draw it, point source or small surface area source. So this is the point source, this is the small surface area source. So here is L over H. So you put the wafer, this is the wafer, and the distance from the wafer center is L, this is L. The height, the distance from the source to the wafer is H. For the typical evaporation height, the distance is 40 centimeter. For the 4-inch wafer, the wafer edge here is 5 centimeter. L equals 5 centimeters, so 5 over 40 equals 0.12. Correspond 0.12 is about here. You can see the film uniformity, I would say 5% film uniformity. So this is the point source. For the point source, so we have the uniform emission of the source material, all the directions. This is called ideal cosine emission. So in this case, so we have this emission deposition rate, but here the n equal to 1. This n number here, n equal to 1. So this is called ideal cosine emission. In this case, if the n is bigger than 1, if the n is higher than 1, so we have this non-ideal, more anisotropic emission from a small surface source. In reality, this one is close to the usual situation. So to get more uniform deposition, we can have higher height, higher distance from the source to the substrate. But this means we need a bigger chamber, bigger pump, lower deposition rate, and more width on the chamber wall. So where to put the source? For the point source, if we have this case, if we have the point source like this, then we put the wafer around it. So for the point source, we put the source here and we put the wafer around a circle. For the small surface source, we put the source here. This is the location of the source. We put the source here and we put the wafer like this. This way we get uniform deposition. So this is the situation for n. This is the ideal case with n equal to 1. So for this situation, you put your source here, and you put your wafer here. It is shown that this Nansen cell behavior is the closest to the experimental result. The Nansen cell behavior means n equal to 1. This is the close to the experimental result. But this is another cell. So you have a vapor here, like gold. You put your gold, we have a vapor on the gold, and we have emission from this small surface. This is the emission from a small surface. So here we have emission from this small surface. So we can show this. For the spherical surface, you draw a sphere here, and you put your source here, and you put your wafer like this. So cosine theta equals cosine phi equals r over 2r0. So cosine theta equals to cosine phi equals r divided by 2 times r0. So this one. Then the deposition rate is given by cosine theta cosine phi equals this one. You can see this is angle independent. So angle independent. So we have uniform deposition on this surface. But obviously, if you look at each particular wafer, you have more deposition here than the deposition on the wafer edge. But overall, the deposition is roughly uniform if you put them along the sphere surface like this. So now we look at evaporation rate. So this is this term. Evaporation rate. So it is given by this formula here. So A is the source area. M is the gram molecular mass. How many gram per mole? T is the temperature, and P is the equilibrium vapor pressure of the vapor pressure inside this nonsense cell. But then here the opening appears as the evaporation source. So how to show this? So how to derive this formula here? So we assume that all the gas molecules move only along plus minus x, y, z direction. So that means we move up, right, left, down, into it, and out of it. So we have totally 6 directions. Then 1 over 6 will move along the plus z direction. So 1 over 6 will move this direction. That can come out. For the opening area A, the area here is A, the area here. The emitted number of the molecules during delta T time is given by 1 over 6, this number here, 1 over 6. N is the number density, molecular number density. A, this is the volume. A area weight delta T. So that means along this height here, this one is weight delta T. So this is weight delta T. So along this height, they will be able to come out. Within this delta T time. So 1 over 6 N A weight delta T. So the per unit emission area, the rate is given by 1 over 6 N weight. So 1 over 6 N and the weight. A is per area, T is the per time. So for the more strict derivation, again we use the Maxwell. We use Maxwell distribution because the molecule actually they don't go along the x, y, z direction. They go all the directions. This number becomes 1 over 4. Here is 1 over 6. So this number becomes 1 over 4 N weight. 1 over 4 N weight. You know N equals to P over KT. Weight is a square root 8 KT over pi m. So this is based on the Maxwell equation. It's similar to what we got here. So here we have 3 KT over m. So here we have 8 over pi. So this similar, close to 3. So 8 KT over pi m, so equal to similar to 3. This is similar to what we have shown roughly. So it's given by this formula here. Now we change the unit from the Pascal, kilogram per mole, a square meter into torr, gram per mole, a centimeter square. So one torr equal to 133 Pascal. So 1 gram equal to 1 over 1,000 kilogram. 1 over 1,000 kilogram. So 1 square centimeter equal to 10 to the minus 4 square meter. So then we have this formula. This is the number of the molecules per square centimeter per second. If we want to convert how many gram, then this time the gram, the weight, the mass of each molecule. So the mass of each molecule is given by how many gram divided by this number Na. So Na is Avogadro number 6.02 10 to the power 23. So then you get this formula here. So this formula is the same as this formula here. So this tells you the evaporation rate per area per time per square centimeter per second, and we know the molecular mass, temperature, and the pressure. So here is the vapor pressure of the common materials. So typically for the deposition we use 0.1 to 10 milliliter. So we can say like we use 1 milliliter. So here, 1 milliliter here. So this is the typical vapor pressure. For instance, from this curve you can see that for aluminum deposition we need about temperature about 1100 degrees. For the case of chromium, for gold we need here 1300 degrees. For the case of chromium, we need a temperature here 1600 degrees. Another thing we know is this melting point. So for the case of chromium, the melting point is 1800 degrees, and evaporation is done at 1600 degrees. So that means that we have the vapor by sublimation, the vapor by the sublimation no melt. So when you do the chromium deposition, the chromium will not be melted because the sublimation gives you enough vapor pressure. We can also do the tungsten deposition at over 3000 degrees. So here are the evaporation properties for different materials. So here are the materials. For example, for chromium, this for the chromium, and this is for the copper, cobalt, all the materials here. This is the minimum evaporation temperature corresponding to 10 to minus 4 torr. Those are the temperatures that give 10 to minus 4 torr pressure. So this is the state of the evaporation. For example, we see that for the case of chromium, so we have the sublimation. For the case of the aluminum, it got melted. The melting point of the aluminum is 650 degrees about. So this temperature, 1000 degrees, the aluminum got melted. So this is the recommended crucible material. The crucible is the container material. So the boron nitride, aluminum nitride, graphite. So normally we use a graphite, just carbon. So here is the deposition rate, angstrom per second. This is the power. So here we assume the distance. We assume the source to substrate distance is 40 centimeters. So now we look at the tools of the evaporation. So here the source material for the evaporation. This one looks like, so we can do evaporation of silicon dioxide. Then the film we got will be silicon OX, and not exactly 2. It's silicon OX. But this one looks like maybe this is the metal. So those may be some compound materials. There are three types of the evaporation. First is the thermal evaporation. So we use resistive heating. Second one is called electron beam evaporation. So we use electron beam to heat up the source. The third one is the inductive heating. So here we have the induction coil. So we have the coil. When we have high frequency coil, like radio frequency coil, this is similar to the case for the when we do the wafer growth. If you remember, for the wafer growth chapter 3, we talk about heating by the inductive coil. So the material here needs to be conductive. If the material here is conductive, then it will induce eddy current. Then you have heating by the eddy current times the resistance. But this one is not popular. So here the resistive thermal, because thermal evaporation means resistive heating. So here we pass the current, and then we heat up. We have the source material inside. But this one typically is good up to 1600 degrees. But those materials, they can be evaporated at temperature below 1600 degrees. So this, for example, chrome will work, but metal like platinum will not work because we need more than 1600 degrees for the platinum deposition. But we can put the material into the crucible like this, into the crucible. We can also use the heated spiral. We put the source material into it, or we can use the dimple. We can use the bolt a small boat. We put the source material into this small boat. Here is the photo of the thermal evaporation. We have the bell jar. This is the vacuum inset. So vacuum chamber. So here inside it looks like this. So this part is the heating part. This is the heating part. So we pass the current. We pass the current to heat up. This is the source material, like a gold or silver. This is the source material here. So in this case, we can do evaporation of 4 different materials at the same time. But this is the quartz crystal. Quartz crystal balance. Quartz crystal balance to measure the film thickness. But this is the cooling water. This is the cooling water. So do you think we need high voltage? Do we need high voltage for the heating? So we know that the heating is given by V squared over R, right? This is the power. So we do not need a high voltage if the resistance is very, very low. So here, when we have the metal, this is the metal, like a copper, not copper, maybe tungsten, high temperature metal, tungsten. So when we have the metal strap, then the resistance is very, very low. Then we do not need high voltage for the heating, but the current will be very high. So the current can be very high. Another one is called electron beam evaporation. So here we have electron beam. We have the filament, tungsten filament, heat up, and we have accelerating grid. This one gives you about 10 kilovolt. So the voltage here is 10 kilovolt. So then we have electrons emitted. We put the bending magnet. So here we have the deflection plate. So we have the electrical field. Then electron will be move around. Electron will be deflected. So this is to rust again the beam across the charged surface, across the charged surface. Then we have magnetic field, bending magnet. Then the electron will be bended to move on the surface. Actually, if we look at this one, we know that we have the magnetic field everywhere along the path, not just along this area. So we need magnetic field everywhere, so it will move in a circular way. So the electron temperature can be extremely high. For example, 1 electron volt gives you 10,000 Kelvin. When we have 10 kilo electron volts, you can see the energy is really extremely high. It will be converted into the electron volt. So the current is 10 to 100 milliampere. So this is good for the high melting temperature metal like tungsten. So we can do electron beam evaporation of tungsten, but not by the thermal evaporation. So the evaporation occurs at the localized point. So here we have only heating. We are only heating in the crucible. So here is no heating. So the crucible is not heated. As a result, the contamination from the crucible is not a problem. We have little contamination from the crucible. But this is different from the thermal evaporation. For the thermal evaporation, all the junk, if we have a lot of junk, if we have junk here, they all come to the wafer surface because everywhere here is very hot. This way you get more contamination. But here, it localized the heating, less contamination. Crucible is not heated, but less contamination. This is the photo of the electron beam evaporation. So here we have the shutter. We put the crucible. The crucible is put inside. The crucible is put inside here, and then we have the cooling water. So typically, the power can be 10 kilovolt. 10 kilovolt. So the current is up to 1.5 ampere. So here we said 100 of milliampere. Then the power for over the area, the heated area is about 1 centimeter square. So the power you can see is very, very high power by the electron beam. That's why we can heat up even tungsten. We can heat up tungsten to over 3,000 degrees for the deposition of tungsten. Here's the comparison of the thermal and the electron beam evaporation. The thermal evaporation is very simple and cheap. We use tungsten tantalum or moly filament to heat the source material. So typically, the current is very high current, but low voltage. So we have the visible light and infrared light irradiation on the wafer surface. So we have contamination from the heated boat or crucible. So as we said here, we have contamination from the junk here. For the electron beam evaporation, it's more complicated and it is more expensive. It can do virtually any material like tungsten, including tungsten. We have less contamination because the crucible is not heated. The substrate is exposed by secondary electrons. So here we have gold, or maybe say aluminum. So here we have 10 kilo electron volt electron. Well, 10 kilo electron volt electron will generate many secondary electrons, and it will also generate X-ray. So when we have high energy electron bombardment on the wafer on the metal surface, we have X-ray. So this X-ray is a big problem because we know X-ray can damage substrate and dielectrics, will lead to the trapped charge. As a result, electron beam evaporation is rarely used. It cannot be used for the MOSFET because the trapped charge can modify the threshold voltage of the transistors. So here is the photo for the containers. All of them can be used for the thermal evaporation. Only this crucible can be used for the electron beam evaporation. For the thermal evaporation, all the 4 cases is used for the thermal evaporation. But this is the resistors. But this one is for the case of chromium. What you see here, black is the chromium. So we pass the current. So here is the tungsten. So we pass the current along the tungsten wire to heat up the chromium. So the chromium is by electro. The chromium is deposited on the tungsten wire by electroplating. This is the heating boat. So we have the boat. We put the material into the boat. But there is the crucible. Those are the crucibles. This is the another thin cell. So we have the box with the small openings. So we have the box with the small openings. This is another thin cell. This one. Here. This is another thin cell. Here. Another thin cell. So the typical materials, so we need high melting temperature for the materials. So we can use tungsten, tantalum, and moly, so they are popular. We can also use graphite or aluminum or boron nitrate. So in reality, this one is the most popular. This one most popular. It can go to very, very high temperature. So this one, the graphite is very cheap. It's about $50 each. So for the graphite, carbon container is about $50 each. For the tungsten container is about $200 each. If we look at the photo here, so this one, I think this is the carbon. This one may be tungsten. So now let's look at how to monitor the film thickness. So we use a quartz crystal. So it's called quartz crystal microbalance. So we know that quartz is a piezoelectric material. That means when you apply the voltage, it will shrink or maybe expand. So when you apply the voltage, it will shrink or expand. So when you apply a DC, when you apply AC voltage, it will vibrate. It will become like this. It will vibrate. So this, we have 6 megahertz, it will vibrate at 6 megahertz frequency. So the resonant frequency will shift. So the amplitude of the vibration will be the maximum at the resonant frequency of this quartz and the electrode materials. This resonant frequency will shift when the film is coated on its surface. If this resonant frequency shift, delta F can be measured. Then we know how much film we have on the surface. So you can imagine the F will, when we have the film here, the F will be smaller because we know F is proportional to 1 over F is given by K is the K is spring constant, M is the mass. So the higher the mass, the smaller the frequency. So we have the film on top, we get smaller frequency. This way we can get the film thickness. So what we need to know is the density of the film. We also need to know another number called the J ratio. We also need to give the J ratio of the material and the density of the material in order to calculate the film thickness based on the resonant frequency shift. So here's the photo of this quartz crystal. This will cost about $10. If you look at here, so this one here is the quartz crystal balance. So this one here, look at it like this. So one issue for the evaporation is the step coverage. So we know that evaporation is very directional. It's called line of sight deposition. So we have this, the vapor comes to here, so you get the coating like this. But it will heat. When it is heated, the material comes to here. It comes to here. Then they can move around. Right? It can move around when it is heated. Or you can also do the rotation. So we do the rotation. You have this deposition here. You have deposition here. In the end, you get more uniform. You get better step coverage by heating and the rotation. So how conformal you can have depend on something called a snaking coefficient, SC. So what is the snaking coefficient? For example, if this one snaking coefficient is given by F reactive divided by F incident. So SC equal to 1, when SC equal to 1, if SC equal to 1, that means the film will get double-rated where they hit the first strike. That means they come to here and they stay here. This means SC equal to 1. If SC equal to less than 1, that means they come to here, they move around. They can bounce back or they can move around. Then we have snaking coefficient less than 1. So we will use the same concept when we do the etching process. For the etching, we also have snaking coefficient. For example, if this one is the atomic fluorine, then we have also snaking coefficient issue. So for the alloy, so one problem for the evaporation is the alloy deposition. Normally, the compound material, then the deposition we have this stoichiometric problem, because the compound material will break down at high temperatures. Then the component, each component will have different vapor pressure. Then the film composition will be different from the source composition. So one solution for this is the co-evaporation. So we have two sources. This is, for example, for gold. This one for the nickel. Then we get, you can this temperature 1, this is temperature 2. Then you can control the flux. You control the flux. You get the composition as you want. So otherwise, if we have the gold nickel compound, we have gold nickel alloy. We have the wafer here. Then you can imagine which material will deposit more onto the wafer at the beginning. So gold will be more than nickel, because if you look at the slide, you see the gold is blue curve, nickel is the red curve. So gold had higher vapor pressure than nickel for the same temperature. So as a result, we got more gold deposition at the beginning. So we have more gold on the wafer, on the film, than nickel. So we can also make use of the shadow evaporation. The shadow evaporation, because the deposition is very directional. It's very directional. You can see, I will make the shadow mask. So here it's called shadow mask. But another name for this is called stencil. This is also called some people call this one as the stencil lithography. So we use a shadow mask called the shadow mask. So we have first deposition along this direction. We can have the we have this structure of the film. Then we do a second material at another direction. We have this black color material. Then we have what do we have here? So what we have here is called, this one has the junction, it's tunnel junction. This can be the Josephson junction. If this is niobium film, then we get Josephson junction. And this is used for the quantum computing. So one way to find the quantum bit, quantum is called the Q bit. Quantum bit is to use the Josephson junction. But to do this, we use this method to make the Josephson junction here. But this is the SEM image of this shadow mask. SEM image of the shadow mask. On the top is the germanium. This is the germanium. So below the film below, so the film below the mask, this one inside here is the polymer. It's called polyether sulfone. This way, when you do the deposition, you can find the Josephson junction to make the quantum bit. So at the University of Waterloo Quantum Nanofab, so we have evaporation that is dedicated for this process, for this shadow evaporation process. So last one is the GLAD, it's glancing angle separation. So this one is mainly done by the Professor Michael Brett from the University of Alberta. So his group worked a lot on this project, on this research project. The glancing angle means this angle is very big. This angle here is like bigger than 80 degrees. So when we have the when we have very high angle, the deposition will get column deposition. So you can imagine. So this is the tiny grain. So this is the tiny grain. This one is tiny. It shows large, but actually, this is the tiny grain. A cluster of atoms formed, nucleated at the first moment of the film deposition, at the random position with random size and shape. So we have this random grains. Then when we have this deposition here, you can imagine we have more deposition on the column and no deposition here. So in the end, this one will grow and bigger and bigger. This will also grow bigger and bigger. So we get this column film. We got columnar film structure, slanted column film structure in the end, because of this shadowing, because of this shadow effect. So this is the normal deposition. Normal deposition, we have this is the texture. Texture of the film. If we do a very large angle, if we do the 30 degree, you get film deposition like this. When you do 80 degree, you get film like this. So in this case, we have this no rotation, stationary surface, no rotation, one evaporation source. This is the chromium. This is the chrome film. So we can play with it. But this is the 86 degree, very big angle, 86 degrees. So you get this column structure. So we can deposit from the left side and also deposit from the right side. So we have two evaporation sources. This is the silicon oxide film. So this is the silicon oxide film. One from the left and one from the right. So more 70% from the right, 30% from the left, you get this column structure. And 50% from the left and 50% from the right, we get this vertical column. And this is very, very loose film. We have loose film. So not dense. So we can play more. So this is what we have seen with the from arrival from the right. So we can rotate. Rotate. In this case, we rotate 180 degrees. So we deposit from the left, then we deposit from the right 12 times. So we get the film like this. And then we do the continuous rotation. We have continuous rotation. You get the film morphology like this. This is the this one combination from this one and this one. So this is the left and the right. This continuous rotation. You get a film like this. You can see. You can play with it. You get this kind of film. For more information, you can look at the web page of this professor. So he has publications. Most publication is from his group. Thank you.